Hi everyone. Today what we're going to do is we're going to change gears a little bit. And so we've been working our way through some radian measure. We've done a full trig in terms of SOHCAHTOA, sine law, cosine law review. And we've dealt with all of our rotation angles. Now what we're going to work our way through is some angle identities and then how we can apply those. So I want to make sure that we've got something just right off the top. That as you think back to your grade 11 year, that identities concept would have been a process in which you would have gone through and you would have proved trigonometric identities. I want to make sure that we're kind of moving away from that a little bit, that we don't associate those two things. Rather, in grade 11, you were responsible for knowing your tan equals sine over cos x, that's called your quotient identity, and you were responsible for knowing that sine squared plus cos squared of any angle equals 1. That was your Pythagorean. And so in knowing those two identities, you would have used those identities to prove others. This year, we add in a bunch of stuff. And where it's going to make a change is the idea that what we are addressing are angle identities. And so if you look back to your grade 11 identities, those two of them, you'll notice that your angle never changes. The tan of some angle is equal to the sine of that angle divided by the cos of that angle. Sine squared of an angle plus cos squared of the same angle equals 1. At no time was your angle changing. What we're going to address this year is the fact that we can affect the angle. And we're going to examine some identities where we can change the angle. So let's take a look at the first one that we're going to go through and we're going to prove. A negative angle identity that we can deal with is given in that sine of negative x is equal to negative sine of x. So very quickly we can notice we can change a negative angle into a positive angle. So that is an identity that is true in all cases. For us to be able to use that identity, though, we have to be able to prove it. We've got to see where it comes from. And so it's not just a blind trust that it is true. So I want to walk through a proof for us dealing with this negative angle identity. And so the first thing that we're going to do is we're going to I know I've given you a circle there and a set of axes, but we're going to kind of work our way through on the left a little bit. And what I want to address is just a right triangle. In the identity, we've been given the sine ratio, and we know that we can always deal with sine ratios if we have a right triangle. So there is my right triangle. Now, if I was to work my way through and deal with this triangle, I may want to hop on to my set of axes. And so what I'm going to do is I'm going to go through and I'm going to draw on a terminal arm on that set of axes, and we can then use that set of axes to work our way through some generic properties. So just to ease and make the diagram look a little cleaner, what I'm going to do is I'm going to draw on a terminal arm into quadrant 1. If I did that, then I'm going to say that I've rotated x, and whether we're talking about degrees or radians, it does not matter. As I've done that, that would then allow me to go through and say that I would hit my unit circle at A. Now, for naming's sake, maybe I'll call the origin here D, and we would be able to work our way through. So how could we end up dealing with it? We could now drop in our height create our right triangle, and I'm going to call the location of that point, point B. Couple things for us as we work our way through. If I was to then try to use that rotation angle and the triangle created to match the original triangle I drew, then I'm just going to go through and I'm going to label using the same names. That triangle would have been created by angle D being X. So, if we're good with all of our labels, then we know that this would have to be side A, this would have to be side D, and this side B, if we were to jump in and look at it as a unit circle, would have a value of 1. Okay, this would allow us to actually create a little relationship on that triangle. And so I could then say that the cos of angle X would be adjacent over hypotenuse. And at the same time, I could say that the sine of X would be opposite over hypotenuse. Now, however you wanted to look at that, we should then be able to simplify those down to cos X is going to equal A and sine X is going to equal D. Now, why is that useful to us? Well, I'm just going to put a little wavy line in underneath there. But the reason why that is useful is that I just found out that side A could be represented as cos X. That means if I jump back onto my unit circle, this side A could be represented as cos X. And same thing on the other side, this side D could equal sine X. Now, why is that important to us? Well, that's extremely important because I can now label the coordinates of point A. How do I get to A from D? I would have to go across cos X units and up sine X units. Now, perhaps that's the sort of thing that you didn't address last year. And that's okay. We can see why it's the case now. But maybe we were unaware that we could actually label the coordinates of any point in our unit circle as cos X sine X. Now, I'm just going to clean up and get rid of that green because we can actually see that property on the triangle outside the circle. Okay. Now, I'm going to ask you to actually fudge your diagram a little bit. The reason for it is what we've now put on that diagram would be information pertaining to the right side of that identity. We have angle X on the diagram. What we need then is angle negative X. Well, to get angle negative X, I would have to rotate the exact same distance or measure, but in the negative direction. And that can be hard to do, to estimate it. But if I was to fudge that a little bit, then what I could do is I could drop the height that I had already created and go all the way down to the circle. And now I could draw on the terminal arm that would take me from point D to the edge of that unit circle. And that allows me to get a pretty decent appearance of what an angle of negative X would be. So we can all just look back on this diagram now, though, and say, oh, well, I was just really, really good at estimating that measure. Okay, if we have that being the case, then I can then label this point as point C, and we should be good to be able to label the coordinates of that. For me to get to point C, I would have to go across cos X units, but I would have to go down sine X units. And so my y-coordinate is negative sine X. Now, for me to be able to walk through that now allows me to work my way through that proof. So I'm just going to shrink this down a little bit. And I could then make a conclusion. that if I go back to my SOHCAHTOA definitions, since the sine of negative x would be calculated as my opposite side divided by my hypotenuse, then my opposite side is negative sine x, and since I'm on my unit circle, my hypotenuse is 1. I have then confirmed that the sine of negative x is equal to negative sine x. So we just gone through and independently proved our first angle identity. That's a negative angle identity. So this is a very important identity because it now gives us the ability to change the sign of an angle if we wish. Using that diagram, though, we can actually create more identities. So we want to examine the other ones. Well, what if we then had cos of a negative angle? That bracket looks a little too much like a C. And we could also work our way through and deal with the tan of a negative angle. So if we were to take a look then at that diagram, we should see that if I had to calculate the cos of a negative angle, that would be my adjacent over my hypotenuse. And if I rotate it in the negative direction, I'm going to get the exact same thing. So what I can see on my diagram then is that the cos of a negative angle is equal to the cos of a positive. And if I was to work my way through my tan of negative x, well, maybe I go back a little bit again and I kind of say like, well, then I know that that tan of negative x would be an opposite over adjacent. So then that means that I would have a negative sine x as my opposite, and my adjacent would be cos x. But that's my tangent identity from grade 11. I know that the sine of an angle divided by the cos of an angle is equal to tan, and therefore that whole thing is equal to negative tan x. So the tan of a negative angle is equal to negative tan of the positive. There are 3 of my identities, and 3 more identities that you need to know. Okay, we're going to pick up the pace as we keep moving, and we're going to add in another 3 identities right away. What you'll see on the top now is we're going to address our complementary angle identities. And so hopefully we're good that if we come out of grade 9 talking about some angle properties, that for us, complementary angles are angles that add to 90 degrees. Now, since we don't really use degrees that much, they're angles that add to pi by 2. And so, if we were to go through and write out the sine, cos, and tan for that triangle. So, what do we want to do then to be able to kind of work our way through that triangle? Well, let's put some labels on it. What we can do is we can call maybe this triangle A, B, and C. And if we do that, then this is side B, side A, and side C. And let's examine it from its angles. So the first angle that I might have in here, I might call generically X. And so I would like you to come up with expressions that represent each of your trig ratios. So we should be pretty quick then to say that the sine of X is opposite over hypotenuse, the cos of X is adjacent over hypotenuse, and the tan of X is opposite over adjacent. Now, how do we end up getting some complementary angles? Well, if we know that one of the angles inside that right triangle is X, then the other angle must be 90 degrees minus X, or pi by 2 minus X. And so what I'd like you to do now is to go through and come up with expressions for each of your trig ratios from the other angle. This time focusing in on pi by 2 minus X. So hopefully we're pretty quick at being able to do that. From the other perspective, I would have B over C, My adjacent over hypotenuse would be A over C. And my tan would be B over A. Well, pretty quickly then, we should be able to make a conclusion based on what we see in the red ratios and what we see in the blue ratios, that we can then draw some pretty important conclusions on this. And so, what do we end up getting then? Well, we should be able to see that my sine of pi by 2 minus x was equal to b over c. And another ratio that equaled b over c was cos x. And therefore, they must be equal. I can also see that I have two ratios here that both equal a over c. And so therefore, the cos of pi by 2 minus x is the same thing as the sine of x. Notice in those two purple identities, I have the ability to change my angle. On the left side, my angle is pi by 2 minus x. And on the right side, it's just x. Now, the last one might be a little uglier because we don't quite have the same expression. But if you notice, your tan expression in red versus your tan expression in blue happen to be the reciprocals of each other. And so, if I was to state then that the tan of pi by 2 minus x was the reciprocal of tan x, then I know that to take the reciprocal of tan x is really cotangent x. And we're just going to write in reciprocal beside. So there are three more identities that we need to know. And you can see where they come from. Now, at the bottom of that page, I want to make sure that we are good to be able to work our way through. That there is also a key component here. And I'd like you to kind of have a pretty big focus. And this would be something that I would want you to be able to reference back to. We have to be very, very careful here. And I want to give you an example of a common mistake that students make when they start to deal with these what we call compound angles. That they may kind of get to this conclusion. And perhaps you can see, first off, the does not equal sign in the middle. But then secondly, what that mistake may be. Like it almost looks like we expanded in our sine. Remember, sine does not exist. That the only way that we can determine a sine ratio is if we have an angle. So sine unto itself has no meaning. So how can we then disprove this? Well, all we need to do is find one instance where this does not equal this. And so what I'm going to do as my check is I'm going to make the substitution of a pretty easy angle to deal with, something like pi by 6. So on the left side then, I would have the sine of pi by 2 minus pi by 6. And on my right side, I would have the sine of pi by 2 minus the sine of pi by 6. And so if I can show that I get a different value on my left side than my right side, then I've proven that that red is not equal. So on the left side, I can do a little calculation that pi by 2 minus pi by 6 is a pi by 3, and I can calculate the sine of pi by 3. Pi by 3 is a big angle, which means it would have a big opposite side. So my sine value is root 3 over 2. For me to calculate the sine of pi by 2, well, I know that the sine of pi by 2 is equal to 1, because that's my vertical y-axis, my positive y-axis, sorry. And I know off by heart that the sine of pi by 6 is 1/2, or pi by 6 is a small angle, so it has the smallest opposite side. There is us using our special triangles. And since we get down to seeing the root 3 over 2 does not equal left side does not equal right side. So what was the whole reason why we went through that process? It's to make sure that we do not ever, ever, ever expand a trig ratio into an angle. Okay, we've got one last angle identity that we're going to cover today, but we're going to deal with it a little differently. So what you see on this page is our next angle identity that we're going to be responsible for knowing. And specifically, it's our cos compound angle identity. So you'll notice within the identity that the cos of A plus B can be written in terms of different angles. So rather than having an angle of A plus B, I can break it into angle A, angle B, angle A, angle B. Now, we would normally, if things were normal circumstances, spend time proving this identity. This identity would take us probably pretty close to 40 minutes to go through in class. It's very detailed. It draws on a lot of information, and we've got a pretty good chunk of algebra we would go through. Given the current circumstances, we're not going to do a proof for this compound angle identity. So unfortunately, you're going to kind of have to believe me and trust me that the cos of A plus B is equal to that right side. Cos A cos B minus sine A sine B. So our job then is to get really, really good at knowing it and being able to use it. So let's see how we can jump in and use some stuff. What you'll see on the screen now is there's your instruction to use your cos compound angle identity to discover what the cos of A minus B is. So we have an identity for what cos A plus B is. Now we need to come up with one for what cos A minus B is. This has a pretty ingenious way. It's actually very simple for us to be able to go through and prove. That if I have cos of A minus B, I could choose to view that as the cos of A plus negative B. Now, why would I choose to use that? Well, the first key feature is the fact that I have an identity for what cos A plus B is equal to. So if I could somehow view what was on the inside not being subtraction, but instead being addition, then I could use the identity I already know. So then I have to go back to some grade 7 integers where I know that adding a negative is the same thing as subtracting. So it's a pretty ingenious and a very simple way to change the way that original expression looks. Well, if it is that case, then I can break down what that red compound angle is using the identity I know. Notice I didn't say expand it. I can break it down. So what does it become? Well, that says that cos A plus negative B would be cos of the first angle times cos of the second angle with a subtraction in between, sine of the first angle, sine of the second angle. So there is me using the given identity to break down my red identity, my red angle. Okay, now my problem becomes none of my original angles in that starred expression were negative. It was just A subtract B. So what I see in my blue line contains negative angles. I need to get rid of those. Well, luckily, I have some negative angle identities. I know from previously, like in this video, that the cos of a negative angle is equal to the cos of a positive. I also know that the sine of a negative angle is equal to negative sine of the positive. And so I can replace those values. Cos of negative b is then equal to the cos of positive b, and the sine of negative b is equal to negative sine of b. Well, I can clean that up a little bit then, and because in that last term, which is the second term, I am subtracting and then multiplying by a negative, I can change that to a positive in between the terms. So, I don't want you spending any time whatsoever trying to memorize those compound angle identities with A's and B's in them. I think it just becomes too much. Instead, let's build it. I want you to notice that the cos of A plus B and the cos of A minus B look very similar. They both contain two terms, and those two terms look the same. The cos of A plus B is cos of the first angle, cos of the second angle, and the next term was sine of the first angle, sine of the second angle. Notice I didn't use A's and B's in my wording. Now, if I also take a look and I zero in on a couple key properties, the first one that I'm going to zero in is the sine in between my angles and then the sine in between my terms. So, the sine in between my angles and the sine in between my terms. And we should notice that they're opposite signs. And so, when I go to break down my green identity, I notice that I have a positive in between my angles, which means I need a negative in between my terms. So if I was to break down that green identity, it is simply cos of the first, cos of the second, opposite sign in between, sine of the first, sine of the second. And I can use that exact same algorithm, that same tool, to break down my yellow angle. So if I have cos of A minus B, then that would have to be cos of the first, cos of the second, opposite sign in between, sine of the first, sine of the second. Now that we've added in those, this becomes your next identity. So previously in this video, we have added in 6 more identities. We just added in 1 more. You now have your cos compound angle identity. So let's see an instance where we can use it. So let's take a look at problem 2. We need to use cos A minus B to prove the cos of pi by 2 minus x is equal to sine x. Now notice that we've already proven this identity today. That's our complementary angle identity. But we now have been asked to use the compound angle to prove it. So we need to use that. Here we go. The left side then was cos of pi by 2 minus x. And what that says then is the cos of an angle subtract an angle is cos of the first, cos of the second, opposite sign in between, sine of the first, sine of the second. Okay, I've now broken down my compound angle. Well, now, where do I go? And one of the mistakes students make quite often, and I think it's all geared because radian measure includes pi in it, is that they mistake when they actually have a constant in an expression versus a variable. I want you to notice that when I circle sine x, I can't calculate that because I don't know how big angle x is. Same thing, I can't calculate cos x. However, when I take a look, I can calculate the sine of pi by 2 because pi by 2 is a value. It's actually a constant. Same thing then with cos pi by 2. But we often make the mistake because maybe we view pi and we almost mistake it for a variable. It's important to know when we can calculate something. And almost any time you can calculate it, do it. Get that in there and make sure that we simplify. So if we were to go through and then calculate those values, well, if I had to figure out a pi by 2, that's me being vertical, then which side doesn't exist? The adjacent. So therefore, my cos of pi by 2 is 0 because I have no adjacent side, and that's what cos asked me to calculate. My sine of pi by 2 then has to be 1. Since there was no adjacent side, my opposite side is everything, and that's what sine is. And then when I calculate that, 0 times cos x wipes that out, and I come in on sine x. Notice what we just did then? We had an algebraic proof to be able to manipulate that expression. So, from today's lesson, there really isn't any practice for you guys to be able to work through. What I want your focus to be is to know those 7 identities cold. Make sure that you could go through and prove the identities for the first 6. We won't worry about our cos compound angle identity. If we can make sure that by the next time we walk into our next video, we've got those 7 identities down, then I think we're doing great. Okay, best of luck.